Alrighty, welcome back. So today we are going to be finishing the optimization section. We're going to start off though with the one homework problem from last time, and let's see, that was number 8. This is section 3.7, and number 8 was, let's see, it was the sum of the first number. I'm going to abbreviate number with the pound sign. I don't want to write it. And sorry, the first number squared. That's kind of important. So first number squared, and the second number is 54, and the product is a minimum. Alrighty. One other little bit of information is the two numbers are positive, so that will help a little bit. Don't have to worry about doing negatives or anything. Alrighty, so the sum of the first number squared and the second number is 54, and the product is a minimum. Well, let's set that up. So the first number is going to be x, so we're going to have the first number squared, so that's going to be x squared. So the sum of that plus the second number, which is y, is going to equal 54. Okay? And the product is a min, so the product is just going to be x times y equals some product. Alrighty? And we want to minimize this, so this equation right here is our constraint. And this one right here is our min-max expression. Okay? So first thing to do is when you want to solve for one of the variables in the constraint, plug it in over here so that we have a constrained min-max expression. So I'm going to solve for y because I really don't want to take the root. So y is going to equal 54 minus x squared. And then I'm going to take that y and plug it in to this y right here. And when I do that, I will have my constrained min-max expression. So let me go ahead and do that. So I'm going to get x times, now y is 54 minus x squared equals p. And I'm going to go ahead and multiply this through and kind of put p on the other side. So p is equal to 54x minus x cubed. Okay? So I have my expression. That is, now this is the constrained expression. And so I am good to go now. All I have to do, I want to find when this is a maximum, so I'm going to take the derivative and then set it equal to 0 and solve. So the derivative of p is going to be p prime is equal to, it's going to be 54 minus 3x squared. Then I'm going to set it equal to 0 and solve. So 54 minus 3x squared equals 0. And so I'm going to divide everything by negative 3 and wind up with x squared minus 18 equals 0. X is equal to plus or minus square root of 18. Okay? So this right here is, I have my two solutions since it was a quadratic, but I know that the x, these two numbers, x and y, are positive, so I can eliminate that negative sign there, and it's just going to be root 18. That's what x is. So now that I know what x is, I figure out what y is, because y is equal to 54 minus x squared, so that's going to be root 18 squared. So it's going to be y is equal to 54 minus 18, which is 36. So I now have my x is root 18, my y is 36. So that means I'll come over here for the last thing. My maximum p is equal to 36 on root 18 x times y. And there you have it. That is the maximum product that you can get. Minimum, maximum. Which one is it? Maximum. Ooh, I think I wrote minimum up here when I meant to just, I was thinking, oh, wait a second, that is a maximum I'm trying to find. Would have been a minimum wouldn't have made a whole lot of sense to be that number, but a maximum makes perfect sense. Now, if I wanted to verify whether or not I had a minimum or a maximum at this location right here where x is equal to root 18, all I would do is just take this value, plug it in to my, well, let me actually do that real quick. It's super easy. You know what? I'm going to make it even easier. Let me clear. I wish I had room. Grr. Let me actually do something odd. I'm going to erase this stuff up at the top so that I can have a little room up here to show you how to figure out if it's a min or a max. Well, one, you can graph it, and that would work just fine. But I've got my x value right here, and I've got my expression right here, my p prime, and that was equal to 54 minus 3x squared. And so I could make a chart where I've got some sort of critical number at x equals root 18, and then do test values on either side to see what I have. But there's another way to do that, and that is to use the second derivative to find out whether it's concave down or concave up. That's a much faster technique, so I'm going to do that. So p double prime is going to equal what? Well, 2, and the 54 is gone, so 2 times negative 3 is going to be negative 6x. Okay? If I plug in root 18, this is going to be p of root 18 is going to be negative, which means it is concave down, which means that at root 18, there's supposed to be an 18, we have a max, which is what we were hoping to have. So that's how you would do it. You just take your expression, take the derivative one more time, plug the value in and see if it's concave up or concave down. That'll tell you if you've got a min or a max. So check, check, homework done. Alrighty, now we haven't even begun to do the cool stuff. So let me clear this and let's get to the really fun stuff. So here we go. Okay, so for this example, and again, all these are word problems, so we have to just kind of, push through it. Let's say that we have an open box. What do I mean by an open box? The top is missing. With a square base, and the surface area. Don't ask me why I just capitalized that A. I have no idea. Surface area is 108 square inches. That's how much surface area we have to have. So I have an open box with a square base, and the surface area is 108 square inches. Okay, that's how much cardboard I have to make this box. Find the maximum volume. Okay, so I've got 108 square inches of cardboard, and I want to find the biggest box that I can make that has an open top. Okay, so first thing I'm going to do is draw the box, because just like with related rates, sometimes it really helps to have a picture, and I'm drawing it with my beautiful artistic way. I've trained in art classes for the past 15 years, and it's finally starting to pay off. Alrighty, so let's see. I've got an open top here, which I'm just going to kind of shade to show that there's nothing up at the top. Okay, I know it's a square base, so I'm just going to call the width and the length Okay, I'm going to call the height of the box h. So I've got my length and width are the same since it's square base and some height. Okay. Now the surface area is equal to 108 inches. Okay. Here we go. How do I calculate the surface area? Well, surface area is going to equal for this box. I'm going to have one bottom, and that area is going to be x squared. And then I'm going to have 4 sides. And each of the sides is what area? It's x times h. So 4x h. Okay? That is my how to calculate the surface area of this box. And I know that that is equal to 108. Okay? Now, this is what? That's right. This is the constraint. Now I need to write an expression that I'm trying to maximize. Well, that's going to be volume. So volume is going to equal, well, volume is length times width times height. So this is just going to be x squared h. And that's what I'm trying to maximize. This is my min-max expression. Okay? So now that I've got this set up, I have to be able to solve for one of the variables in my constraint and then plug it in over my volume. Okay? You can solve for x or h, but looking at that quadratic there, I really don't want to solve for x. So I'm going to go ahead and solve for h. So if I do that, I'm going to start off with, let me just rewrite it here, plus 4x. You know what? I'm actually going to go over here and start using the full spread. So I've got x squared plus 4xh equals 108. Alrighty. So 4xh equals 108 minus x squared. And then h is just equal to 108 minus x squared divided by 4x. Okay? It looks bad, but it's not. I'm going to take this compound expression here and turn it into 2 individual terms. So it's just going to make doing the derivatives a lot easier. H is equal to, well, 108 divided by 4 is 27. So I'm going to have 27 over x when the dust settles. And then minus, I'm going to have x over 4, right? X over 4. That is a much nicer expression for my h. Now I'm going to take this h and plug it into this h right here. Okay? So if I do that, I'm going to get v is equal to x squared times 27 over x minus x over 4. Okay? Well, that worked out really nicely. Now I'm going to distribute. I'm going to get v is equal to, well, I'm going to wind up with what, 27x here? 27x minus, I'm going to move that 1/4 to the front just because it's going to make the derivative really easy. X cubed, 1/4 x cubed. And this is now what? This is my constrained mm expression. Okay, so that's what we need to be able to take the derivative of and set it equal to 0 and solve. So if I do that, let me swing up here, little barrier there. Let's see, I'm going to get v prime is equal to, well, 27 minus 3/4 x squared. Okay, that is my v prime. Now I can take the derivative of that, not derivative of that. I can set that equal to 0 and solve. So 27 minus 3/4 x squared equals 0. I'm going to multiply everything by negative 4/3, just so I can get rid of this. If I do that, I'm going to wind up with, what's that going to be, 36? Yeah, negative 36 plus x squared equals 0. X equals plus or minus root 36, which is just 6. Now, here's the beautiful part. In the real world, we can't have a negative length or width. So if it is an actual measurement, that negative is not even there. So I can just say x equals 6 straight up. So now I know what my x is. How do I find what h is? Well, h is this expression. I could do this one or this one. E1's fine. I think I'm going to do this one. That's going to be a lot nicer, I think. So actually, you know what? It's not going to matter. We'll do it anyways. So h is going to equal 108 minus, well, x squared is going to be 36 divided by 4 times 6 is 24. So 108 minus 36 is 72 divided by 24, which is, drum roll, h equals 3. Okay, so what is the maximum volume? The maximum volume, V, is equal to x squared, which is 36, times 3, which is 108. Now, that is just a happy coincidence. There's no deeper meaning. I'm actually looking through, I wasn't expecting that. That was not expected at all for it to be that kind of value, but let's see if that holds. I think that is, I'm looking at the actual solution that I have here. Okay. Yep, that is correct. Cool. It's just a happy coincidence that it happened to be the same as the surface area. That's not a standard thing that happens. That's just something that happened to happen this time. So that is my maximum volume with 108 square inches of surface area of cardboard or whatever. I can make a box that contains 108 cubic inches. Pretty cool. That's it. And tell me how you would figure that out any other way. You can't. It's not going to happen. That's what makes these optimization problems so awesome. So now that we've knocked out kind of a cool one, let's clear this and move on to a even more interesting one. Alrighty. So this next one is, I can probably say it's in my top 5, maybe top 10 calculus tricks, what we're about to do. So we clear this. I've cleared it. Now let's move on in. So for this example, pay super close attention to what's going on. This is one of the questions that's going to be, that is on the take home. And it's if you remember absolutely nothing from the optimization section, this is a good trick. Like, that's not true. Remember all of it. This is useful stuff. If you want to know how people know that when they've found the min or the max of something, they've maximized their profits, they've minimized their costs. It's a derivative expression like this. It's an optimization problem. So pay close attention to this one. Here we go. Which points on y equals 4 minus x squared are closest to 0.02. So what I have is, if I graph this thing out, let's see, really opening down, what is it? Y is 4, so that's going to just be 1, 2, 3, 4, and then 1, 2, 1, 2. So it's going to be a parabola. If you can, you didn't see anything. It's a parabola that looks like this. This point right here, if I could have drawn it correctly, is at 0, 4. This is at 2, 0, and negative 2, 0. Okay? Now, I want to know at the point 0, 2, what points on this curve are closest to this value? I hope that's at least somewhat impressive that we're about to solve this problem. Because it can be any values on the curve, but there are two numbers. There's going to be one on this side and one on this side. So it'll be a positive x value and a negative x value are going to be the closest possible points to 0, 2. So how do we do this? Well, this one is a little tricky. We have to be a little creative with this. This right here is, here we go, constraint 1. And this right here is going to be constraint 2. Why 2 constraints? Well, let's say I didn't have this one. What points are on this graph are closest to nothing? It's just, I need two things for this to make sense. What point, if I had just had this one, what points on are closest to this point? Well, I have no function to find. So when you're trying to find the closest point between the closest point on a function to a given point, you have to have both of these constraints present in your min-max expression, okay? Now, what expression do we use for our min-max expression? Well, this is the key word right here. Closest means min distance. Would you agree? Hopefully. So, I'm going to bust out the old distance formula. So, distance formula. Hopefully y'all remember this. If not, you can derive it from scratch using the Pythagorean theorem, but hopefully you remember it. We've got d is equal to square root of x2 minus x1 squared plus y2 minus y1 squared. Y'all remember that one? Now, that's my distance formula, and I somehow need to, this is my min-max expression right here. So this is the mm expression. Okay? I need to plug both of these constraints into this expression right here. So how do I do that? Well, I'm going to rewrite this distance formula just a little bit. I'm going to rewrite it as d, actually, you know what, I'm going to come over here again. Maybe I'll solve it all on one page. D is equal to square root of x minus x1 squared plus y minus y1 squared. Why on earth did I do that? Well, it's the same thing. It's just written in a form that's going to let us do substitutions in a lot more believably than it would be if I just tried to shoehorn in everything into this one. All I did was I just rewrote my x2 and my y2 as x and y. Okay? So now what I'm going to do, I'm going to plug in constraint 2 first. I'm going to call this x1 and this y1. Okay, so I'm going to plug those values in. D is equal to square root of x minus, well, 0 squared plus y minus 2 squared. Okay, so now I have the second constraint plugged in. Now I need to get this one in. Where does this one go in? Well, this one goes in right there into that y. So I'm going to wind up with d is equal to square root of, here we go, x minus 0 squared plus 4 minus x squared minus 2 quantity squared. Okay, so now my y expression has been substituted in, and look what just happened. I now have a distance formula that has been constrained with both constraints and is a function of x only, which is really, really nice. So I'm now going to kind of combine terms, square everything, gather like terms, and see what I get for my expression for d. So the distance is going to equal square root of, well, we're going to have, this is just going to be x squared, right? So x squared plus, this is going to be, when the dust settles, 2 minus x squared quantity squared, right? 2 minus x squared quantity squared. So distance is going to be root x squared plus, it's going to give me 4 minus 4x plus x squared. Okay? X squared, my gosh. If I had good sense, that was a square right here, isn't it? That is not right. This is a square. This is to the 4th power. I'm going to change my brush size or I'll wipe everything else. So this is to the 4th power right here. Okay? So I'm now going to combine my x squares and wind up with d equals, I'm going to rearrange things to be in descending order, x to the 4th minus 3x squared plus 4. Okay? Now, this is finally, after all that work, our constrained min-max expression. Okay? There we have it. Now, the next step is where it's going to get a little bit interesting. If you allow me, I'm going to clear this off. I have a little bit of room to work. I don't need a lot, but I don't think I can fit in right here. So I've got my distance is equal to square root of x to the 4th minus 3x squared plus 4. Okay. Now, I need to take the derivative of this. And so if I wanted to, I could say this is x to the 4th minus 3x squared plus 4 to the 1/2 power. And the derivative would be 1/2 times all of this to the negative 1/2 times the derivative of the interior, 4x cubed minus 6x. And when I rewrite that, that's going to be d prime is equal to, well, I'm going to wind up with 4x cubed minus 6x over 2 on the root of x to the 4th minus 3x squared plus 4. Alrighty, so I can set this equal to 0 and solve, because d prime equals 0. Here we go, we got practice with this, right? That implies that just the top is equal to 0. 4x cubed minus 6x equals 0. Okay? I can factor out a 2, let's see, what do I want to factor out? I'm going to factor out an x. So x, I can even do a 2x if I want. 2x, I'm going to be left with 2x squared minus 3 equals 0. And I'm going to wind up with x equals 0. And 2x squared minus 3 equals 0 means that x squared equals 3/2. X equals square root of 3/2. Okay? Oh, sorry, plus or minus. Now, notice I have a positive x value and a negative x value. This right here is what we're looking for, because this kind of makes sense. If you look back to the graph, which I'll sort of sketch out, I had something that looked kind of like this. And then I was looking for the points that were closest to this number right at this point. If I draw lines coming out from there that hit the graph at a right angle, guess what the x value for this point is? Oh, I can actually write it. Square root of 3/2. Okay, guess what this x value is? Negative square root 3/2. Okay, now I just need to find what my y value is. Well, what in the world was y? Well, y, from my original function, y is equal to 4 minus x squared. So y is going to equal 4 minus root 3/2 squared. It's just 3/2. So y is going to equal 5/2. 5/2. 5/2. Those are the 2 points that are closest to the function from the point. I really hope you enjoyed that. That is just insanely satisfying that we're able to find the points that are on this function that are closest to this point. Wow. Now, one thing I want to say before I leave is something to kind of look out for. The math that I did here is 100% correct. It is rock solid. It works that way every time. But there's a little bit of a shortcut you can do with this. Okay? Let me go back to right here. I had d is equal to square root of x to the 4th minus 3x squared plus 4. Okay? I'm looking for the minimum distance. Okay? This distance is minimized when this is minimized, when the expression inside the root is minimized. Okay? So a root is minimized when the stuff under the root is minimized, which lets us go straight into, if I wanted to, this is kind of like a pseudo different distance. This is, I don't know, d sub 2 maybe. It's going to just be the stuff that's in the interior, minus 3x squared plus 4. So if I have that, then my d sub 2 prime is going to be negative 6. How in the world did I mess that one up? Go me. It's going to be 4x cubed minus 6x, right? Well, that's what we got here anyways. It's the same thing. But if you want to skip the part where you have to take the, you have to rewrite it in the form of a fractional exponent, do the power rule with the chain, rewrite things to where you have what's up top, set that equal to 0 and solve. Just go straight for the stuff that's interior. That's going to be your new pseudo D, and then you're going to wind up minimizing that value, and you'll get exactly the same thing. So just you can skip that. You're completely authorized to skip that step and go straight into just minimizing the stuff that's under the root. Okay? Alrighty, so that was that. Now, let's do one more example. So let me clear this. Okay, so for our last example, it's a little bit easier than that one that we just did. So we'll finish with a nice simple one. Let's find a rectangle with perimeter equal to 72 inches and the volume is maximized. Is a max. Okay, so you can imagine I've got 72 inches of fencing, I've got 72 inches of chain, whatever. I need to form it into a rectangle, but I want to maximize my volume. Okay, so how do I do that? Well, we start off, we do our first off we draw the picture, right? Because that's going to guide us. So I'm going to call this O, X, and Y. How does that sound? So what is the perimeter? Well, the perimeter is going to be, if I walk all the way around, so that's going to be 2x plus 2y equals 72. And that is my constraint right there. Okay, now I need the volume as a max. Well, that just means that V is equal to X times Y. So now all I have to do is solve. This is my my min-max expression, and I just need to solve for one of these constraints, one of these variables in my constraint, and then plug it in. I'm going to solve for y just because why not? That was, sorry. Let's do 2x plus 2y equals 72. See, 2y equals 72 minus 2x. Y is equal to 36 minus x. Okay? So, now that I have that, I can take and plug that in to this y right down here, and I'm going to get v is equal to x times 36 minus x. Okay? V is equal to 36x minus x squared. And this is now my constrained constrained min-max expression. Okay, so now I can take the derivative and solve. V prime is going to equal 36 minus 2x, set that equal to 0. 36 minus 2x equals 0. X equals 18. Okay? So if x is equal to 18, what's y? Well, y is equal to 36 minus x minus 18. Turns out y is 18, which means we don't have a rectangle, we've got a square. And it turns out that is always going to be the case. If you're trying to maximize volume, max volume is always a square if you're talking about a rectangle. There can be things that can kind of throw that off. For example, if you have the max volume of a box, an unconstrained box with all sides own is going to be a cube or a cube. But as soon as I take one of the top part off, as we saw with the first one that we worked today, that's not necessarily so. So just keep an eye out. If you have a rectangle, a complete rectangle, the maximum volume of that is always going to be a square. And if you have a three-dimensional rectangular solid, the max volume of that is always a cube. It just is. So there you have it. That is kind of going through all this. It didn't take too long to go through the remainder either. I'm going to give you two problems that we'll tackle next time. Let's see. The two problems are, if I can find them, 16 and 19. So tackle 16 and 19. So homework, and this again is 3.7 still. Try 16 and 19 and see how it goes. And then the very next video, we'll go over that, and we are going to start in on chapter 4. Finally. So super excited. Alrighty, y'all have a wonderful day, and I will see you later. Stay safe. Bye-bye.